Hello friend, in this video we will create a game. For this we will use the principles and techniques on which the Wolfenstein 3D game is built, and also stylize it as a Doom game. In other words, we will create a symbiosis of these games. So, in order to create such a game, we need to know that Wolfenstein 3D is based on the raycasting algorithm. In reality it is performed on a two-dimensional plane, but at the same time it allows you to get a three-dimensional illusion of space, so to speak, pseudo 3D. We will take a detailed look at each stage of the game creation. We will make an efficient and fast 2D raycaster. With the help of a raycaster we will get a 3D projection of our game level. We will learn how to properly apply various textures and embed sprites, and we will also make smart and full-fledged enemies in our game, from which you can't hide anywhere due to the pathfinding algorithm. So, let's begin. We will create our game using the Pygame library, so we install it using the command presented on the screen. The initial structure of the project will consist of 5 files. This is the main file and then the files player, object renderer, raycasting, map and settings. The settings file will store the main game settings, so let's first define the screen resolution and set the framerate for the game. And now you can go to the main file and write the main application template. Here we import the Pygame library, the system module and the settings. Let's create a game class in the constructor of which we initialize the Pygame modules, create a screen for rendering the set resolution and an instance of the clock class for framerate. We need a new game method, leave it empty. In the update method, we will update our screen, and display information about the current number of frames per second in the window caption. In the draw method, at each iteration, we will paint our screen black. Then we need a run method in which the main loop of the game will be. From this loop we will call the update and draw methods. We will also create a method for checking events. Here we will check the events for closing the working window and for pressing the escape key, and if such events occur, we will correctly exit the application. And this method will also be called from the main loop. Now it remains to create an instance of our game and call the run method. Let's run the program and make sure that everything is working properly. A black window of the set resolution is created. So now let's create our game world. For this we go to the map file and make our map. This will be a two-dimensional array in which digital values will mean walls and false values will be empty space. For a better perception of the map, I marked them as underscores. Now let's write a map class where we get an instance of the game class as input to the constructor, and the minimap and world map become attributes. This world map will be obtained through a separate method in which we iterate over our array and write the coordinates of elements with only numeric values to the dictionary. Let's display our map on the screen. For this we will write a test method draw. Iterating over the world map, we will draw each element of the map as an unfilled square. So now you can go to the main file. Here we import the map file. Create an instance of the map class in the new game method, and make a call to the new game method from the main application's constructor. Let's make a call to draw the map from the draw method and let's run the program. And as you can see now, we got the correct display of the given map in gray. Before moving on to the player file, let's set the initial settings for the player. We will define the position of the player on the map, the angle of his direction, the speed of movement and the speed of rotation. Then in the player file we import the settings file, and we also need the Pygame and math modules. Let's create a player class, in the attributes of which we will take an instance of the game, x and y coordinates of the player and the angle of his direction. Let's write the movement method and for now leave it empty. We will call the movement method through the update method. And for convenience, we will make 2 properties. The first returns the player's coordinates, and the second integer coordinates to know which tile of the map we are on. So what about the movement of the player? It should be made standard for first-person shooter controls. In simple terms, we need to make the WASD keys control the movement, and also make the player's direction control. And since we are on a two-dimensional plane, let's take a closer look at what we should do. Let's imagine that we press the W key, then knowing the angle of the direction of the player and the speed of his movement, we can calculate the increments dx and dy by which the player's coordinates need to be changed, and for this, as you can see from the slide, we use the trigonometric functions of sine and cosine. And of course, we can similarly calculate such increments for all other keys. So let's use this information and go to the movement method. We calculate the sine and cosine values from the player's direction angle, then set dx and dy to be 0. And here comes another important point. If we want the player's movement speed to be independent of the frame rate, then we need to get the delta time value for each frame. Then in the main file, the delta time value can be easily obtained in the update method through an instance of the clock class, which was created to set the frame rate. Now we return to the player's file and correct for the speed taking into account the delta time. We also pre-calculate the product of the obtained speed by the calculated values of the sine and cosine. Next, we obtain information about the keys pressed in, according to the above theory, calculate the increments dx and dy. Now we need to apply the received increments to the corresponding coordinates of the player, and it remains to implement the control of the player's direction. For now we will do this for pressing the left and right keys, while the angle value should remain within 2p. As in the case of the map, we will similarly write a test method for drawing a player on a plane. We will draw his direction of movement as a line, and the player himself will be in the form of a circle. So let's go back to the main file and import the player file. Then we create an instance of the player class and need to call two methods. The first method is update, and the second method is draw. Now we can run the program and see how our game works. And as you can see, the player's movement occurs as suggested. So the player movement occurs at a fixed number of frames per second of 60. Let's check the player movement if we turn off the fixed frame rate. So let's start again. And notice now the frame rate is 10 times higher, but the player's movement speed has not changed. This is where the biggest advantage of using delta time lies. And now it doesn't look good when we pass through walls. Let's implement a check for player collisions with walls. To do this, go to the player's file and first write a method that checks if the checked coordinates hit the wall. We then use this method in the collision check method. Using the computed dx and dy increments in turn, we check the new coordinates, and only allow movement if there is no wall. Let's use this method instead of changing the player's coordinates and see the result. As expected, now the walls have become impassable and we can say that we have completed the preparatory stage of our game. And now we can move on to more interesting things. And now we are starting to write the engine of our game. So let's go to the raycasting file and import the Pygame, math modules and the settings file. Next, we will write the raycasting class, in the attributes of which we take an instance of our game, and define the raycast method, which will be called from the update method. And now let's talk about what raycasting is in our case. So the whole point of raycasting comes down to the fact that we need to cast a given number of rays in a certain field of view of the player. And for each ray we need to determine the intersection point with the wall. But with what step should we move the ray into the depth of the map? And here we can take advantage of the fact that our map is a grid. To do this, we need to find intersections with vertical and horizontal lines, thus the ray will have the most optimal number of steps. And here we should consider intersections with vertical and horizontal lines as two separate cases. If we consider the intersection of the ray with the verticals, then we can see that the ray along the x-axis moves to a distance dx equal to the size of the tile. We have it equal to 1. In this case, the movement along the y-axis also goes in equal segments dy, but their value must be calculated. In the case of horizontal lines, the opposite is true. dy is equal to the size of the tile, and dx needs to be calculated. It is also important for us to determine the depth delta so that we can calculate the distance to the wall for each ray. So to go further, let's set the settings for raycasting. We will define the field of view of the player, the number of rays. For the whole game it is enough to take half of the resolution width value. Also, based on the number of rays, we will define the angle between the rays, delta angle, and define the maximum depth. So let's say draw distance. In the raycast method, we calculate the angle for the first ray. We need to subtract half the value of the field of view from the player's angle, and add a small value in order to avoid the division by zero error in further calculations. Now let's write a loop on the number of rays, with the help of which we calculate the angles for each ray. And we also need the coordinates of the player on the map, OX, OY, and the coordinates of his tile, X map, Y map. In the loop, we calculate the values of the sine and cosine of the current ray and proceed to the case of the intersection of the ray with verticals. First of all, by the value of the cosine of the ray angle, it is necessary to determine the x-coordinate of the intersection with the verticals, x-vert. If the cosine is positive, then x-vert will be 1 more than the x-map value. But with a negative cosine value, x-vert will not be equal to x-map, since we need to check the left tile, so we subtract a small number from x-map. And here, by the value of the cosine sign, we will determine the value of the variable dx. After that, if we examine the resulting picture in detail, it will become obvious that using trigonometric functions we will calculate the value of the distance of the first intersection with the vertical, depth vert, and the value of the y-coordinate, y-vert. So we are at the orange point and we need to get to the blue one. Again, if you draw all the details, it will become clear how to determine the depth delta value and the dy value using trigonometry. Thus, we have everything we need to cast a ray and find intersections with verticals. We will cast the ray in a cycle by the number of steps equal to the value of the maximum depth. Here we first determine the tile based on the x-vert and y-vert values, and then we check that we did not stumble upon a wall. If this happened, then we break the cycle. If not, then we cast the ray further using the dx dy values, and calculate the total value of the ray depth. As for intersections with horizontal lines, we do similar detail work here, first calculating the depth and coordinates for the first intersection, and then also calculating the delta depth and dx values to cast the ray for this case. So, as a result of all these calculations, we have 2 points of intersection of the ray with the wall, and it is obvious that the depth that will be less and will be what we are looking for. So let's determine the depth we need. And also here, for debugging, let's try to draw the entire result of raycasting. Okay, let's go to the main file, import the raycasting file, create an instance of the raycasting class and call the update method. Let's turn off the drawing of the direction of the player's movement and look at the result. So now we can observe the work of our raycasting in action, as we see no problems arise and it works correctly. Well, now we are all set for the next step to get a 3D projection in our game. So at the moment we have a calculated value for the depth at which the walls are located. To get the projection of objects on the screen, you need to place this screen at the correct distance from the player. If we draw in detail the placement of this screen, then as you can see from the slide, we can get the distance we need using the tangent function. This will be the ratio of half the resolution width to the tangent of half the value of the player's field of view. Let's go to the settings file and calculate half the resolution value for the width and at the same time for the height. And then we can calculate the correct distance for the screen location. And now we need to determine how we calculate the projection height of the walls. To do this, let's look at the whole picture from the side. Again, if we draw everything in detail, then we can see 2 similar triangles that are formed from the player, the wall and its projection height. From the similarity property of these triangles, we can say that the ratio of the size of the walls to their distance from the player is equal for both triangles. And since our wall size is equal to 1, the projection height will be equal to the ratio of the distance at which the screen is located to the depth at which we see the wall. Okay, let's go to the raycasting file and calculate the projection height according to the above theory, but we take into account the addition of a tiny number to the depth in order to avoid the division by zero error. Let's try to draw our walls, and for this we will use the Pygame function to draw rectangles. But then we need to determine the scaling factor. Since the number of rays we have is less than the screen resolution in width, this is done specifically to maintain better performance. Then, taking into account the scale, we will draw a white rectangle, place it according to the number of the ray along the x-axis, and in the center of the screen, taking into account the projection height. Now let's turn off the drawing of the map and the player, and look at the result. Well, here we got our first pseudo 3D projection. We can walk around the map and see everything, But let's add depth to the lighting in our game. I suggest to do this, calculate the color in some power dependence on the value of the depth of the ray. Thus, our game began to look more interesting. But pay attention that at a close distance to the walls they become convex. This is the so-called fishbowl effect. It occurs due to the use of the Cartesian coordinate system along with the polar one. To eliminate this drawback is quite easy. For this we multiply the depth value by the cosine of the angle, which we get by subtracting the value of the ray angle from the angle of the player's direction. So we check that the flaw is eliminated and the walls look correct. And in this way we got the classic raycaster. This can be said to be our engine for all further innovations, of which we will have quite a lot. In the current step, we will look at applying textures to our walls, but first of all we need to load these textures. I created a resources folder and the texture folder is located in it. It now contains 5 texture files. And first of all, in the settings file, we will define the size for the textures in the game and calculate half of its value. Now let's go to the object renderer file and import Pygame in the settings file. We will create an object renderer class that will render all objects in the game. We will take the game instance and the rendering screen as attributes of this class. For convenience, we will create a static method for which the path to the texture and its resolution are specified. This method loads the texture from the specified path and returns a scaled image. And now we can write a method for loading textures. It will return a dictionary in which the texture number is the key, and the texture itself is the value. On our map, the walls are marked with numbers. They indicate exactly which texture to apply to the wall. We will access textures for walls through the wall textures attribute. Here we will call the texture loading method. So, in order to have access to textures now, we import the object renderer file and, before raycasting, create an instance of the class of the same name. So as for texture mapping, now our image is built from rectangles, the height of which is equal to the calculated projection height for a given ray, and the width is equal to the scale size. So, we will cut out exactly the same rectangles from the texture and draw instead of the current ones. This is the main idea of texturing in raycasting. But we still need to understand how to calculate the texture offset value. For this we will consider all 4 cases for the ray when it reaches the wall. We consider 2 cases for verticals, when the value of the cosine of the ray angle is positive and negative. And we do the same for the horizontals for the sine value. And as you can see, the calculation of the texture offset value will always depend on the angle of the ray and the collision with the vertical or horizontal side of the wall. Okay, then let's go to the raycasting file. In the constructor of this class, we define the attributes for the result of raycasting, the objects to be drawn, and we define a short name for the wall textures. Next, in the process of raycasting, we determine the numbers of the textures of the walls into which the rays collided. We do this for both cases with horizontals and verticals. Now, based on the calculated depths of the rays, we find the actual texture number, and here we calculate the correct texture offset in the way that was announced above. At this point, we can delete the previous rendering of the walls. This is no longer necessary. And in the list of raycasting results for each ray, add a tuple of the depth value, the projection height of the wall, the texture number and its offset. And the most important thing is not to forget to clear this list before starting the raycasting itself. So now we need a method to get objects to draw. Here our task is to get the parameters calculated as a result of raycasting, and based on them, for each ray, select a subsurface in the form of a rectangle from the initial texture. To make it clear, you can see the size options of this rectangle on the slide. After that, we scale the subsurface to the projection height, calculate the position of this column texture based on the ray number, and add it to the list of objects for rendering. We need the depth value, the wall column texture and its position. We call this method in the update method and go to the object renderer file. Here, using a separate method through an instance of the game class, we will get access to the list of objects for rendering. iterate over this list and draw the resulting texture columns on the rendering screen. We call the work of this method through the main draw method, and it remains in the main file to also call the draw method on the object renderer instance. Let's run it, and as you can see we got nice textured walls. It looks very decent. But we can notice that when we get very close to the walls, our performance drops catastrophically to almost zero. This is due to the fact that with such an approach to the wall, the depth of the ray tends to zero and the texture begins to scale in height to very large values. To eliminate this performance hit, we need to consider a special case where the projection height of the wall exceeds the height resolution of the screen. In short, we need to calculate the height value for the texture column. This value will be such that when scaling the texture, its size will not exceed the screen height value, and thus we will get rid of resource-intensive actions, unlike the standard scaling for the first case. Let's run and compare the performance. As we can see, now getting close to the wall we no longer see such a drop in performance, but at the same time the image becomes very pixelated due to the fact that our player has no size, as it is made in the form of a dot. Let's define some scaling factor for the size of the player in the settings file. Then we go to the player file and we need a method to check for wall collisions. Here we will divide the value of this coefficient by the delta time. We do this because the increments dx and dy depend on the delta time, but the size of the player should not depend on this delta time value, because we will find the product of these values. If you look at how it works, now in the game you can already feel that the player has a size. And at the same time, there is no strong stretching of the texture when approaching the walls. You can even more clearly see the operation of this method through the 2D view of our game. Here you can already see for sure that the player has a certain size. And by the way, since we have different types of textures loaded, let's change the designations for the walls on the map and see how it looks. Well, now we see that our game world has changed for the better again, and we have the opportunity to set the desired textures. But as a first-person shooter, there is no mouse control right now, so let's implement it. In order to make smooth mouse control, in the settings file we define the sensitivity for the mouse, its maximum relative movement and the left-right border on the screen. Let's write the mouse control method in the player file. Here we get the mouse coordinates, check if the x-coordinate is within the bounds, if not then set the cursor to the middle of the screen. Then we get the value of the relative mouse movement since the previous frame and clamp this value. And as a result, we will change the angle of the player's direction to the value rel, taking into account the values of sensitivity and delta time. Let's make a call to this method from the update method, and disable the control of the player's angle using the keys. And as you can see, we now have full control for our game using the keys and mouse. And to hide the mouse cursor, in the game class constructor, disable it with the appropriate command, and you can check the game again. Also at this stage, you can diversify our world by adding the texture of the sky and color the floor. Let's add a seamless sky texture to the textures folder and define the color for the floor in the settings file. Then we can load the added sky texture. The appearance of our sky will depend on the movement of the mouse, so we define the initial offset for it equal to 0. Next, we will write the draw background method. Here we will calculate the offset depending on the relative mouse movement value for the player instance. Using the blit method we will place two sky textures, taking into account the calculated offset value. And it remains to draw the floor in the form of a rectangle of the assigned color. We call this method through the main draw method and, by the way, it is no longer necessary to fill the screen with black. Let's run the game, and well, we got a pretty nice background with which the game becomes more and more complete. But as you can see, in our game, apart from the background and textured walls, there is nothing else, so now it's time to fill our game world with interactive objects. So it's time to add sprites to our game. To do this, let's create a new file called sprite object. And we also need to place the sprite we need, let's say, in a new folder called static sprites. So let's import Pygame in the settings file. Let's create a sprite object class. The input of the constructor is the path where the sprite is located and its location on the map. In the attributes we take the instance of the game in the player, the coordinates of the sprite, we also load the image of the sprite and create attributes for its width and half of this value. And let's write the getSprite method, which we will call from the update method. The first thing to do is determine the theta angle, which is the angle the player is looking at the sprite. This is found using the arc tangent of the ratio of the difference between the player and sprite coordinates. Then let's find the difference between these coordinates, and calculate the theta angle using the addend2 function. And now we need to find the delta angle. This is the difference between the theta angle and the player's direction angle. And with the help of the delta, we can find how many rays our sprite is shifted relative to the central ray. So we find the delta angle, but if you do more complex work, you will understand that if the condition shown on the screen is met, the delta angle must be increased by 2p. Now we calculate how many rays in the delta angle, and as a result, we find the x position of the sprite on the screen by adding these rays to the central one and multiplying by the scale value. To calculate the size of the sprite's projection, we need to calculate the distance to the sprite and remove the fishbowl effect for it, as we did in the raycasting file. And to maintain the performance of the game, we will do further calculations if the position of the sprite is inside the visible part of the screen and not too close to the player. So, we will find the projection of the sprite in a separate method. As in raycasting, we will calculate the height of its projection, but here we must take into account that the sprite initially has a different aspect ratio, so we will determine the image ratio and, taking into account this coefficient, we will adjust the correct projection size. Then we scale the sprite to the calculated projection size, find its position on the screen, taking into account that it does not disappear when its center is outside the edges of the screen. And the most interesting thing is that we will add this sprite to the array of walls that is obtained from the results of raycasting. Since we have introduced many new attributes, in order to avoid errors, we will define these attributes in the constructor of our class. Let's test how the sprite is rendered. Import the sprite object file, create an instance of the class and call the update method. And we observe a rather strange picture. Our sprite is visible through the walls, although it is correctly in its place. To fix this problem, before rendering all objects, it is enough to sort our list by the first element in tuples. In these elements we just have the values of the distances from the player to the walls and sprites. Let's check. And now we see the correct rendering of the sprite, but at the same time the sprite seems to be hanging in the air, and the question also arises: how to set the size of the sprite if it does not fit initially? To do this, we will introduce two more parameters, scale and shift, to the input of the sprite object class constructor. Let's assign them to attributes. Obviously, if we multiply the resulting projection size by the scale value, then the size of the sprite will also change accordingly when drawing. Let's reduce the size of the sprite by half and check. And as you can see, this method works great. It remains to figure out the height shift. Then you can multiply the projection height by the shift value, and add this result to the sprite's Y position. And as you understand, for each sprite, such settings are selected individually, but they need to be done only once. Thus, we got a working way to display sprites in our game. But what if we want to draw more interesting things, let's say animated sprites? So, to get started with animated sprites, you must first prepare. In this case, you need a set of sprites. If you change them one by one, you get a fire animation. I placed them at the address indicated on the screen. We will create an animated sprite class that will inherit from the sprite object class. Here, the constructor will receive all the same parameters except for the new one, the animation time. And first we call the super function to run the constructor of the parent class. We will also take the value of the animation time into the attributes. But for further work with this class, we need to import the OS and DQ modules. So we need the path to the folder with our sprites, and we will load them using the getImages method. We will store all images in an instance of the DQ class, Then using the OS module we will get access to the names of all files in the folder indicated by the path, download the images and place them in the queue. We need to define in the attributes, let's say, the value of the previous animation time and the trigger to perform the animation itself. Then we will write a method for checking the animation time. Here we will compare two time values, the current and the previous one. If the difference between these values is greater than the animation time, then we assign the true value to the animation trigger. So, to perform the animation of the object itself is quite simple. If the trigger has a true value, then we rotate the queue of images by one element and assign the self-image attribute to the first value from the queue. And from the update method, we will first call the update method of the parent class, and then we will call our two methods. Let's check. Then create an instance of this class, and call its update method. Thus, now we have the ability to add animated sprites, which in turn decorates our game world even more. But it's quite inconvenient to add sprites to the game in this way, so I propose to create a class from which all objects in the game will be processed. Let's call it Object Handler. Import the sprite object file and write this class, the attributes of which will be the game instance, the list of sprites, and specify the paths to the corresponding folders with sprites. Let's create a method for adding a sprite to this list, and in the class constructor we will have, so to speak, a sprite map, where we will add our sprites to the game. And we will make an update method where we will call the method of the same name for all sprites in this list. Then we do the same, import this file, create an instance of the Object Handler class, and call the update method. Let's start the game, and make sure everything is working properly. And then we get a way to conveniently arrange the sprites in the game. For example, to make it clearer how to use this method, I added another animated sprite. So at this stage, we have already managed to diversify our game enough with the help of static and animated sprites, but as you understand, our game now lacks interactive, so let's move on to even more interesting things. Let's implement a weapon in our game. For this we will create a file of the same name, and by the way, I placed the files with the animation of the shot and reload in the path indicated on the screen. So let's create a weapon class that inherits from the animated sprite class, while specifying in the parameters only the path, scale and time of the animation. For weapons, we don't need to calculate the projection size, so we just scale all the sprites to the specified scale value. We also need to calculate the position of the weapon, given the scaled sprite size, so that the weapon is centered on the screen. Then add the draw method where we draw the weapon, and write the update method while leaving it empty. Import the weapon file, create an instance of it and call the update and draw methods. And now you can already see our weapon, but for now it looks like a static sprite. In order for our weapon to fire, we first need to trace the event of the actual shot that the player fired. And besides, we need a Boolean variable of the shot itself, initially with a false value. So in the single fire event method we listen for the event when the player presses the left mouse button. And in the event that the value of shot is false, we assign it a true value. Now in the weapon class, we need attributes for reloading, the number of sprite images and the frame counter, and in addition we will define the damage for the weapon. Next we need an animate shot method. Here if the reloading value is true, then we will assign a false value to the shot variable for the player instance. Then we perform the standard frame by frame animation, but at the same time we count the number of frames. And if this number of frames is equal to the number of sprites, then we return a false value to the reloading variable and reset the counter. But before calling this method, you need to make a call to the method for checking the animation runtime. Then, in the single fire event method, add a check that there is no reloading now, and to start the shot animation, assign this variable a true value. Let's start the game, and as you can see, When you press the left mouse button, a single shot occurs and then a reload animation, while we cannot make the next shot until the animation ends. And everything seems fine, but right now I would like to hear the sounds of our weapon. And to do this is quite simple. Let's create a file called sound. According to the path indicated on the screen, I placed the sounds necessary for the game. In the class itself, you need to initialize the sound mixer and load the file we need. Let's import this file and create an instance of the sound class. Then every time we fire, we can access this instance and play this sound using the play method. And now you can not only see the shot animation, but also hear it. Well, as obviously, shooting at empty space is not very fun, so let's populate our game world with different enemies and monsters. At this point, we will implement enemies in the game, then we create an NPC file, and look at the folder structure where the sprites are located. I've put together 4 folders containing sprites for attack, death, idle, pain, and walking animations. And also placed a separate file with the initial sprite. So we import the sprite object file and several functions from the random module. The NPC class itself will be inherited from the animated sprite class, and at the input of the constructor we will specify the parameters already known to us, and then do not forget to call the super function. First of all, using the getImages method, we will load all the sprites for animation from the folders voiced at the beginning. And then we will define a number of parameters for the NPC. We will include in them the attack distance, its movement speed, size, amount of health, damage dealt, hit accuracy and Boolean parameters whether the NPC is alive and in pain. Let's write the update method and for now call the methods to start the animation and get the projection of the current sprite. So, to display our NPC, we will use the object handler class. Here we will create a separate list for NPC and write the path to the corresponding folder. For convenience, we will make a method for adding NPC to this list. And then we will create an instance of the NPC class and add it. And similarly, we will call the update method for all enemies in this list. Let's start the game and make sure the NPC is displayed correctly. For now, the enemy is just looking at us, and then the first thing that can be implemented is the behavior of his inaction. Okay, then the whole logic of the NPC will be based on whether he is alive or not, so just turn on the animation of idle images. Now the enemy behaves as if he is inspecting everything around, and the next step is to make him react to our shots. Well then let's write a method in which we check if the player fired a shot. Then we need the NPC position on our screen to be in the center, taking into account its projection value in width, and in this case we stop the bullet and set the pain variable to a true value. We will create a method to animate the pain, let it happen within one animation interval. And based on the call to the hit test method in the NPC, we will call the pain animation or further use the idle behavior. So let's start our fun. As you can see, when hitting an enemy, an animation of pain is shown, that is, everything is functioning properly. And by the way, at this stage, in the sound class, let's load the rest of the sounds that will be used in the game. Then let's add the sound of pain when hitting the NPC and check the result. As you can see, we now have sound effects and the game becomes more fun. But there is a very significant drawback. Let's try to shoot through the wall. And as we understand, our walls in the game do not stop the shots. Now we need to do raycasting again, but only for one ray between the player and the NPC, that is, we need to find out if there is a line of sight between them or not. To do this, we will need almost the entire code of the raycast function until the projection is calculated. We will copy it from the raycasting class. So we need to first check if the player is in the same tile with the enemy. You also need to enter variables for the distances to the player and to the walls, for verticals and horizontals. The angle between the NPC and the player is known to us. This is theta angle. We raycast for one ray, and if this ray hits a wall or an NPC, then we will record these distances. We do the same for the case with verticals. And in the end, we will find the maximum values of these distances and, based on this, we can determine whether there is a direct line of sight between the player and the NPC or not. And to make it clear how this method works, let's draw such a result of raycasting as an orange line. Then we will run this drawing from the update method, and again look at our game in 2D mode. Let's test it, and now we can tell exactly when the NPC sees the player. And it will have a fundamental application in the further implementation of the NPC logic. Then we will return everything back, and turn off this drawing. In the case when the NPC is alive, we can get the raycasting value and write it to a separate variable. And now add a line of sight check in the NPC hit method. If we check the shooting at the NPC from behind the walls, we see that they have become impenetrable. So it is obvious that when hitting an NPC, he should be deprived of health by the value of the damage of the weapon. And at the same time, you need to make a method for checking his health. In the case when the health ends, the NPC is no longer alive and you can play the sound of his death. We also need an NPC death animation that only plays once. For this we will use the frame counter and compare its value with the number of sprites for this type of animation. And of course we will include this method in the NPC logic when it is no longer alive. Well, let's now finish off our NPC and look at the animation. And as you can see, everything seems to be working correctly, but the animation itself is rather slow, since the entire animation depends on the value of one animation time variable. And in order not to create new methods for timers, you can do it differently. We will make one global trigger. Here we will define a user event and set a timer for this event of 40 milliseconds. And then this global trigger will take true value only when the number of the assigned event appears in the list of all events. And now we can return to the NPC death animation method, and here we change the value of the animation trigger to the value of the global trigger. So let's see how the animation changes with this approach. And it's not hard to see that the animation is much faster, so this is also one of the good ways to create timers. Let's implement movement for the NPC. Let's say let it move to the position of the tile where the player is. Then we calculate the angle for the NPC if he looked at the center of this tile. And knowing this angle, you can calculate the increments for the x and y axes, and to start the movement of the NPC, we apply to these increments the same methods for determining the collision with the walls that we used for the player. In order for the collision checking method to work correctly, only the size of the enemy itself must be taken into account, since here the increments do not depend on the delta time. We will turn on the movement animation in the case when there is a direct line of sight to the player, and here we will use the movement method for the NPC. So let's check how the movement of the enemy works. As expected, if he sees the player, he starts moving towards him. But as soon as we go behind the wall, the enemy stops moving and behaves as if he did not see anything. Here I propose to create some kind of player search trigger, which will take on a true value as soon as the enemy sees us. And then even if the enemy has lost sight of us, he will continue to move towards the player. Do not forget to define the player search trigger in the constructor of our class. And let's look at the behavior of the enemy again, but only in the 2D game mode. So when the enemy saw us, he starts moving towards the player, and as we can see, he continues to look for us even if we hid from him. But the behavior of the NPC looks very stupid. He just rests against the wall and, in principle, cannot get around it. And here pathfinding algorithms will come to our aid. Let's create a pathfinding file. Here we will create a class of the same name, in which we need to define the ways of moving to neighboring tiles. For the enemy we will allow diagonal movement. And the first thing we need is to build a graph of adjacent tiles. It will be a dictionary in which the coordinates of each tile will correspond to a list of adjacent tiles, that is, from which tiles we can get to the original one, and for this we will find this list with a separate method for which we use the list of our ways. Next, we will write a method for the classical breadth first search algorithm. And the essence of the algorithm under consideration is that we put the initial tile in the queue and form a dictionary of visited tiles. Then in a loop until the queue is empty, we get the first element from it and get all adjacent tiles, and if they are not in the visited dictionary, then we put them in the queue, and at the same time we write information about which tiles we came from to the current. So it remains for us to restore the path from the initial to the desired tile, that is, from the NPC to the player. At the same time, we do not need the whole path, but only one tile for the next NPC step. Then let's go to the main file, import pathfinding, and create an instance of this class. And now we can go to the enemy's movement method, and using the pathfinding instance we will call the method to determine the tile for the next NPC step. And for clarity, draw this tile in blue. So, after our NPC saw the player, he turned on the search mode, and as you can see, the enemy can now chase us bypassing any walls. Thus, the use of pathfinding algorithms takes the behavior of the NPC to a more advanced level. But I wonder what will happen if we add a second NPC and look at their joint movements. And as a result, although both enemies move along the shortest path, they eventually merge into one point, which again looks somehow stupid for our game. And the fastest solution to this incident will be to create a set to store the positions of the tiles where all the NPC are located, if they are alive of course. Then, in the pathfinding algorithm, we will not take into account such positions as a possible direction of movement. And in addition, we will add the same check to the position of the tile for the next step. If we now compare the movement of the enemies, we can say that it differs significantly from the previous one, at least they begin to move more intelligently. Although this is not an ideal solution, you can think of other ways, but let's stop there and move on. Let's get out of 2D mode and bring our 3D projection back. And now we will write a method for attacking the player. For now, let's just make a shooting sound with an animation time interval. But we will use this method only when the distance to the player is less than the attack distance, and here we will turn on the attack animation. Also, do not forget to turn off the 2D display of enemies, and you can look at the result. And as we see when approaching the NPC, they activate the animation in the sound of the attack, and at this stage we have all the loaded animations for the enemies embedded in the logic, but still we do not have full interaction with the player. We are now in the last phase of game development where we will implement full player interaction with NPC, and also make complete and interactive gameplay. Enemies can't hurt us at the moment, but initially we gave NPC a hit accuracy value. Therefore, we can supplement the attack method. When the random value meets the accuracy requirements, then we will call a certain method for taking damage by the player. Then in the settings you can define a value for the player's maximum health, and take this value into the attribute of the player's class constructor. Then we will write the getDamage method, in which we will reduce the player's health by the damage value. And at the same time, you can designate damage as a kind of blood screen. In this case we need a suitable image. I will use a semi-transparent red image. And it remains to overlay this image on the rendering screen of our game. And by the way, in the method of getting damage, we activate the playback of the sound of pain for the player. So if you look at the result, you can see that if the enemy hits us, a red picture appears and the sound of pain is played, which has a good enough effect on the perception of receiving damage. But in order to draw the amount of health the player has, I picked up images with numbers and a % symbol in the style of the game. Let's load these images and scale them to a suitable size for the game. And also we will make a dictionary where each number will correspond to the desired picture. Then we can write a method in which we convert the health value into a string, and iterating over it, we can use this dictionary to display the amount of health in the upper left corner of the screen. Now you can use this method and look at the gameplay. And now it becomes possible to monitor the health status for the player, but now we need to make the end of the game in the case when the player dies. So we need a method where we check if the health is over, create some end of game screen, and here we will need to update the rendering screen, make a small delay and call the new game method. Let's call this method from the getDamage method, and now we need some picture to indicate the end of the game. Load this picture and create a method for overlaying this picture on the game screen. Now we just have to wait for the enemies to finish us off. And as you can see, after such an event, the game restarts again, which is what we need. And in principle, we have everything ready, but I would like to talk about a few more interesting things. Suppose now you can implement some timer by analogy as we did for animated sprites. In the new method, based on the results of this timer, the character's health will be checked, and if it is less than the initial value, then it will be restored by 1 unit. Thus, if the player takes damage and manages to hide from enemies, his health will gradually regenerate. And to make it clear to you how to create other NPC, then let's go to this file. And if you have sprite sets for enemies, then creating new ones is very simple. Just inherit from the NPC class we created and specify the parameters and attributes that you would like to endow a specific NPC type. Thus, we can make the game even more rich and diverse in terms of gameplay.